Okay, so we know yesterday we discovered from the graph what the derivative of sine x was and cos x. Today we're going to prove it from first principles. So if you think back, this is exactly what we did first unit. We did everything graphically to get an idea of what derivatives look like, and then we did it from first principles using limits to come up with some patterns. So when I'm telling you the derivative here, I want you to at least see where it came from first principles. We saw where it came from with the graph, which was pretty convincing. This is going to be equally convincing, and this is all just so that you can move forward and say, okay, I know what the derivative of sine is, I know what the derivative of cos is, and I just go off and use the rule. I don't think you'll be expected to duplicate this, but I do want you to understand it. So you can think that this would be a good thinking question that I might not ask you to reproduce, but ask you questions about it. So we're going to just do sine x, and we'll do cos x next. So first we're going to try and differentiate from first principles of sine x. So we're going to use that formula from the beginning of the year. So we're going to go off and do the derivative of sine x. That means wherever we see the function, we're going to replace it with sine x. So it's still the limit as h approaches 0, and the function is sine. So it's sine, but instead of x, it's x plus h for the first part, minus f at x, which of course is just sine x, all over h. So we're going to use a lot of the stuff we remember from last course. So what we have right here is a x plus h. We're taking the sine of an x plus h. Well, if you think back, and this you don't need to write, you can write off to the side. If you think back to last semester, we had a compound angle formula, which was a connection of two other angles of sine a plus b. And if you think back to then, sine a plus b was sine a cos b plus cos A sine B. So let's remember that from last course, last semester, and use that in this compound angle. So I'm just going to group that, move it off to the side, and we can use this as a little side note here to remind us on what we're going to do on that. So again, limit as h approaches 0, but we're going to expand the compound angle formula there. Instead of a plus b, it's x plus h. So it'll be sine of the first, so sine x, cos of the second, plus cos of the first, sine of the second, minus sine x, that's tagging on there, and then all over h. Okay, so that one, maybe if you thought about it and said, hey, I remember something like this before, you can go from here, or go from there. From here, though, I don't expect you to know what to do next. This is just a trick that I learned when I learned this proof. But what we're going to do is we have this really big fraction here. It's all over h. I'm going to break it up into smaller parts. I'm going to break up the first part. So it'll be the limit as h approaches 0. So I'm going to break the first part up. I'm actually going to gather this term and this term and bring them together. So sine x cos h minus sine x. I'm going to put that all over h. And then I'll leave what's left over as its own little fraction over h. It's a fraction, so I can break it up into two smaller fractions, or different fractions. They have this common denominator of h, so it doesn't matter if I split them up or bring them all together like I did in the line before. So I just took two of those and brought those over. The reason I did that is because these terms right here have a common factor, and that factor is sine x. So I'm going to take it out. If I take it out of the first term, I'm left with just a cos h. If I take it out of the second term, I'm left with a 1 all over h plus cos x sine h over h. Now I'm going to use one of my limit rules from the limit rules that you learned or self-discovered in the assignments at the beginning after Unit 1. You did a rule on, or an assignment on limits. There you discovered that if you're taking the limit of a sum, you can take the limit of each of the terms. That's what we have here. We have a sum, this thing plus this thing. So if I'm taking the limit of a sum, I can take the limit of each parts of that sum. That's what I'm going to do on this line. So it's the limit as h approaches 0 of sine x cos h minus 1 all over h, and plus the limit as h approaches 0 of the second thing, which is cos x sine h over h. The other property was that if I have anything that doesn't have an h in it, since I'm only investigating the limit as h approaches 0, I can bring out the stuff within the brackets that doesn't have an h in it. So you see this sine x here doesn't have an h, so it's not going to be influenced by the limit. So that limit, that sine x part can come out front. So this here can come out front, and I can only investigate the parts that have h in it. Because if I actually took the limit, sine x isn't going to change because it doesn't have an h. Same thing in this one, except the thing that doesn't have an h in it is a cos x, so I'm going to bring it out front, because it's not going to be influenced by the limit either. These two steps, going from here to here and here to here, are from the properties of limits that you self-discovered in the assignment that I gave you at the beginning of the year. Now the next part is kind of a bit of investigation. Okay, so the next part is we want to investigate what this limit is. And this limit, because we don't have any ideas of what these functions look like. So we'll use again some of the techniques that we discovered in that assignment in Unit 1 to investigate what the limit of these functions are. And to do that, we're going to use the graphing calculator. So instead of you grabbing them, I'll just use the one up here, and you can watch. So what we're going to do is actually put in this function. So we'll go to y equals, and we'll do cos of bracket. Instead of h, I'm going to have to use x. Oh, I don't need that bracket. X minus 1. I'm going to need to put this whole thing in brackets, so this top part is in brackets. So it's cos, on the top half is cos x minus 1, and then the bottom half is just divided by x. In order to see this on the graphing calculator, I'm going to have to change my mode to radians. And then we'll graph it, and we'll see. So a pretty interesting function. I get a pretty good sense of what it does. I think I might change my window so I can see it a little better. I think if I go to like -2 and +2, that should be helpful. Oh, I changed the wrong thing. Sorry. Go back to window. I wanted to keep this as -9.4 and 9.4. I wanted to change my y, excuse me, to -2 and 2. There we go. So there's the shape. We have an interesting cosine function. Um, we could investigate what the function itself does, and that would take a while. But all I'm really interested in is the limit as h approaches 0, or in this case, x approaches 0. So I want to really investigate what's happening around the 0. Remember, when we're investigating limits, we have to investigate the left side of the limit and the right side of the limit. So if we look at this, we can see that the left side of the limit has it coming down to 0. You see the function from the left-hand side comes, and it comes down to 0. So from the left side, it appears this function goes to 0. And then what does it do from the right side? Well, the right side, it does the same thing, and it comes to 0. Which means the limit of this function must be 0, because it's equal from the left side as it approaches the right side. So the conclusion from the graphing calculator is that the limit as h approaches 0 of cos h minus 1 over h apparently is 0. We get this from the graph calculator. That's true. It turns out there is. We could zoom in really close if we wanted to really investigate it, but it does. From the left side it comes to 0, and the right side it comes to 0. So I can evaluate that limit. So when I go back to my formula then, that means that whole thing will change, and this will be just sine x, and it'll be times 0. Okay. So now the question is, what does the sine function do? So I'll go back to my graphing calculator, I'll go y equals, and now instead I'm asked to find the sine, so I'll replace that with sine. I don't have a minus 1 at the end, so I'm going to delete that. So I have sine x over x. So I wonder what that graph will look like. And again, we have it doing some very interesting things, but again, we're interested as the limit approaches 0. So we're going to look from the left-hand side and the right-hand side. Again, from the left-hand side, the function comes up and it gets right to that spot. And the right-hand side, the function comes right up to that same spot. And looking at the ticks, I think that's 1. I'll just push trace to confirm. And there, yeah, it looks like it's approaching 1. Now, just like with a cosine function, you actually see there is no y value. Oops. We see how there's no y value at x equals 0. And we know that that's true because, look, there's going to be, if you actually evaluated the function there, it won't work. Same with this. It won't work. That's why we have to take the limit. So we know from the left it approaches a value, and from the right it approaches a value. How close is it? Well, we see that it's pretty close to 1. Just to the left, it looks like it's 0.99. Just to the right, it's 0.99. So we can make the assumption that if we take the limit here, that the limit is actually 1 for the sine curve. So the limit as h approaches 0 of sine h over h is 1. And so we can replace that into our equation and go cos x, and this whole thing is 1. So again, we needed the limits in order to do this. We couldn't just substitute in h equals 0. It's not allowed. You see that it doesn't exist on the graph. But if we take the limit, we know that the limit itself, that imaginary, as close to that as I can get without actually getting it, that imaginary limit is indeed 1. So if I go back to my solution then, and my proof, I've just made this whole question a lot easier. Sine x times 0 is 0, and cos x times 1 is cos x, and so it turns out that the derivative is cos x. So therefore, f prime at x is cos x, which is what we discovered yesterday. So that's good news. It worked out yesterday, it worked out graphically, and today we're able to apply first principles to get the same answer. So now my question is, what about the derivative of cos? Well, you could do the whole long proof Same way that we did right there by taking, from first principles of cosine this time, splitting up the fractions, taking the limit of each side, checking the calculator what it looks like, and hopefully we get the correct answer. But what I'm going to do is, since I now am convinced and I have a proof for the derivative of sine, I'd like to be able to use it to prove the derivative of cosine. So how am I going to do that? Well, I'm going to ask you to think of a way that you can change a cos function into a sine function. And of course, it's one of those formulas that we used last semester. So I'll give you for a second, maybe talk with your elbow partners to decide if you can remember how to change a cos into a sine. Maybe everyone's just staring at each other and we don't know. So I'll remind you that we do that by taking 90 minus the angle, or in radians, it's pi over 2 minus the angle. This is sine pi over 2 minus x. Remember, every cos value has an equivalent sine value of 90 minus that number. So remember, the cos of 30 is the same as the sine of 60, because it's 90 minus 30 is 60. The cos of 10 is the same as the sine of 80. If we do it in radians, instead of 90 minus, it's pi over 2 minus x. So that's the complementary identity. From last semester. So if cosine can be expressed as sine pi over 2 minus x, then I'm going to take the derivative of that. So now I'm going to take the derivative of this, and the derivative of sine whatever is cos whatever times the derivative of the inside. So in this case, it's the derivative of sine is cos, and then you have to differentiate inside. Well, differentiating inside is just a constant, so the derivative of pi over 2 is just 0, minus x. Well, the derivative of minus x is just minus 1. So naturally, this minus can come out front, and we get minus cos pi over 2 minus x. And if we think about it, we're going to use the same complementary identity to go backwards. So we used it here and said that every cos can be expressed as a sine. Well, we're going to do it again and change this cos pi over 2 back into the sine. And therefore, f prime at x is negative sine x when the original is cos. And again, we discovered that yesterday from the pictures. Now we're able to say that it's also true from the algebra. So why did we do this? Well, we want to just have that background knowledge. We want you to see the proofs and have that experience, be able to comment on it. Like I said, I'm not going to expect you to reproduce this. I just want you to understand it and maybe comment on how or where or why it happens. And that's the purpose of this video. The rest of the class will be mostly giving you more time to practice the derivative of sine and cos in various questions, like the ones we did yesterday.